Good morning, students. Let's continue the chapter thermodynamics. In previous lectures, we have seen the terms which are related to thermodynamics, and now we are going to study one of the most interesting topic of thermodynamics, and that is the PV diagram. What is this PV diagram? PV diagram is a graphical representation of equation of state of a system. What is PV diagram? PV diagram is graphical representation of equation of state of system is called PV diagram. What is it? It is simply a graphical representation. Simply graphically we represent the state of a system, and that representation is a PV diagram. Let us consider a equation W is equal to integration of dW, where the limits of integration they are from V1 to V2. Let's substitute the value of dW. What is it? That is P dV. This is the integral which represent the work done in expanding a gas from volume V1 to V2. The work done is found by two ways. One, by knowing the exact relation between pressure and volume, and another way is by knowing the path of the system between the limits of integration. This is the path between the limits of the integration, from which volume to which volume that the system is get changed. Now this integral represent the total work done, and as it represent the total work done, area under PV curve represent the total work done. Now let us see two cases in which there is expansion of gas, and in another there is compression of gas. Suppose these are two PV diagrams. P came first, so it is along the vertical axis, and V came next, so it is along the horizontal axis. So this is the PV diagram. Now let us consider this should be the initial state and this should be the final state. These are the two states. This is initial state A, this is final state B. At initial state, the volume is V1. As the horizontal coordinates come first, we get volume V1, and then the pressure is P1. So the coordinates are volume V1 to pressure P1, and the system changes from A to B, and now in this case the volume is V2 and the pressure is P2. So the coordinates are volume V2 and then pressure P2. These are the coordinates, and suppose this is the path. Suppose this is the path. In this path from A to B the system goes. Same points are here. This is point A and this is point B. This is point B. Same path is there, but in this case in reverse direction, in this direction. So the initial point is A and the final point is B. The coordinates of the initial points, they are V1. Okay, they are getting interchanged. V2 become V1. V2 become V1, and the final volume, that is V2, and the pressure is here P2 because it is second point, and here the pressure is P1 because it is the first point. So these coordinates are V1 P1 and V2 P2. The integral that represent the work done, and the work done is the area under curve. So we are interested to find how much area is under curve. In both the two cases, this is the area under curve. Okay, this is the area under curve. In both cases, the area under curve is the same, but the work done, they are having different direction. In first case, the volume is get increased from V1 to V2. So this is the expansion of gas. What is this? This is the expansion of gas. And in second case, the volume is get decreased. So this is the compression of gas. And in expansion, work is done by gas. By whom? By gas on piston. So as the work is done by gas, it is positive. And in the second case, work is done by piston on gas, and so the work done by gas is negative. In this case, the work done is negative. Now let us consider a third case. In this third case, suppose we are having the same PV diagram. This is P and this is V, but in this case, suppose the pressure is kept constant. Suppose this is the initial state and this is the final state. The initial volume is V1 and the final volume is V2. The pressure is constant and that is P. So the coordinates of this are V1P and the coordinates of this is V2P. These are the coordinates. Definitely the area under curve is get increased, although the volume change is the same. The volume change V1 minus V2, this is the change, and this is the similar case as that of this. The volume go on increasing, and as volume go on increasing, again this is the case of expansion. And so in this case also, the work done by gas is positive. So this is about the PV diagram. I think you know something about this PV diagram, and now let us see the next point, that is the work done during a thermodynamic process, which is our next point. Our next point is work done in thermodynamic process. How much work is done in the thermodynamic process, that we are going to see. What is thermodynamic process? When the state of a system is going to change, that is thermodynamic process. Now let us see, this is our PV diagram. This is the P axis and this is the V axis. This is the pressure and this is the volume. Okay, I will shift here. This is the pressure axis and this is the volume axis. Suppose this is the initial state and this is the final state. This is state A and this is state B. Initially the volume is suppose V1. And finally the volume is V2. And initially the pressure is P1 and the final pressure is P2. These are the 2 points. And suppose the system go in this way, in this direction. This is the path of the system. This is the first way that system, the changes occur. In second case, suppose the pressure is kept constant and volume go on increasing, and at this point the pressure suddenly drops and it become P2. At this stage the volume is constant. So this is the second way. And in third way, suppose the volume is kept constant and pressure suddenly drops, and then the pressure constant and volume go on increasing. This is our third way. Now we are interested to find how much work is done in these three cases. Now let us see first the work done is in first case. This is our PV diagram. So this is our initial point A, this is our final point B, and this is the path. Okay, this is the initial volume, this is the final volume. Volume changes from V1 to V2. So the area under curve is this much. This much is the work done. This much is the work done. This area under curve that represents the work done by the system. Now in second case. This is our pressure axis, this is our volume axis. The initial point is A, this is initial point, this is final point, this is initial point A, and same is the final point B. But path is different in this case. Initially the pressure is constant and then suddenly drops. So this is the second way. Now let us find the area under curve. This is the volume V1, this is the volume V2, this is volume axis. So this is the area under curve. As this area under curve is increased, the work done is also get increased. And now let us see the third case. In the third case, this pressure axis, this volume axis, this pressure P, this volume V, this initial point A, and this is the final point B. In this case, the pressure suddenly drops and then the volume go on increasing. This is the third path. Now we are interested to find the work done. This volume V1, this volume V2. So in this case, this is the area under curve, and from these three graphs, from these three PV diagrams, we can conclude that work done is different. Work done in this second case is the highest, and work done in the third case, that is the lower. This is the intermediate in between these two, and from this we conclude that work done is not a state function, but it is a path function. The work done is not depend on the state, but it is depend on the path. And now let us apply this thermodynamic process to our first law of thermodynamics. What is that first law of thermodynamics? First law of thermodynamics is change in internal energy is the difference between heat supplied to the system and the work done by the system. This is the change in internal energy. This Q is the heat which is supplied to the system, and the W is the work done. Now let us see here the PV diagram. This is our PV diagram. This is initial point A. Okay, and suppose we are having two cases. In first case, this Q is 0. This P axis, this V axis. Q is 0 is meaning is that the heat is not absorbed by the system, or heat is not transferred from the system. And when heat is not absorbed or heat is not transferred from the system, the temperature remain constant. When temperature remain constant, the pressure remain constant. There is no change in pressure. So if we go in this way, or if we go in this way, the pressure is constant. And that's why Q is V. Only the change in internal energy due to the work done. So if we go in this way, then the work done W is positive, because the work is done by the gas, and that's why this is positive. And as this is positive, del U is decreases. If we go in this direction, del U is decreases. The change in internal energy is decreases. And if we go in this direction, this is the compression, then the work is done by the piston on the gas, and that's why if we go in this direction, del U is increases, because this is negative, positive, and this is 0. So del U in second case, that is go on increasing. Now let us see second case. Suppose we are having this work done W is equal to 0. Work done W is equal to 0 means there is no change in volume. Volume is in this direction. in this direction, the volume, then the work done is 0. And if we increase the pressure, then this Q is go on increasing, and when this Q go on increasing, then the internal energy is go on increasing. So in this direction del U is get increase, and if we go in this direction, then the pressure decrease. That means the heat supplied to the system that decreases. So in this direction del U is negative. So this is the region, this is the region, this is the quadrant. We may say that if you go in this quadrant, then the change in internal energy del U, that is definitely go on decreasing. And if you go in this quadrant, in this direction, okay, if that final point is somewhere in this region, then the change in internal energy del U is positive, that go on increasing. And these are not we not sure that whether that change in internal energy is increase or decrease. That will depend on the values of heat supplied and work done in these two regions. Okay, that's all. Thank you.